Hey guys, so today we're gonna start 12.1, which is where we're gonna start working with the three-dimensional coordinate plane and stuff like that. So go ahead and grab your notes and let's get started. Um, so let's see, 12.1, 3D coordinate plane. Goodness. All right, that's an E, I promise. Okay. So first off, just some notation. There's a couple different things we talk about with the three-dimensional coordinate plane. So we know that R, like that funky R with the line through it, is the set of real numbers. And then R2 is the two-dimensional coordinate plane. So the XY plane typically. And then you might have guessed it, R3 is going to be the three-dimensional coordinate plane of real numbers. Okay, so we're going to be working in R3 now for actually this whole chapter. And sometimes you'll also hear it called like three space. That's just another way to say three-dimensional space. Anyways, so what it typically looks like when we draw the three-dimensional coordinate plane. Grab another color here. So you've got your XY plane down here, crossing there. And then we've got the z-axis right here. So it's going to be an x, y, and z for our variables or for our coordinates. So we have the x-axis, the y-axis, and the z-axis. And so within all of these, we've got the bottom here. If you think of this as kind of a three-dimensional room or something like that, the floor would be the xy plane. This right wall over here would be the yz plane. And this left wall over here would be the xz plane. Okay, so that's kind of how we think about and visualize and draw a three-dimensional coordinate plane. Also, the direction of the the z-axis, the direction of the positive z-axis is determined by something called the right-hand rule. And you might have heard of the right-hand rule before in like a physics class or something. If you've talked about vectors before, you might have heard about and talked about and thought about something called the right-hand rule. Okay, so basically, if you put your hand along the positive y-axis with your fingers pointing at the origin, kind of like that, and then you curl your fingers in the direction of the positive x-axis, the direction of your thumb is going to be the direction of the positive z-axis. So if you want to kind of write down those directions real quick, put your hand on the positive y-axis with your fingers pointing at origin. Curl your fingers in the direction of the positive x-axis. Then your thumb is in the direction of the positive z-axis. Oh, and of course this is your right hand. but it's called the right-hand rule. So hopefully that was kind of self-explanatory there. So that's how we determine when we're drawing a three-dimensional coordinate plane what direction the positive z-axis is going to go. Okay, the other thing that we need to know when we're talking about the three-dimensional coordinate plane is kind of how to refer to coordinates. It's going to be in an ordered triple. So we've had ordered pairs in the two-dimensional coordinate plane. So again, three-dimensional is not going to be all that different. If we have our coordinate plane drawn out, let's say we've got a coordinate out here somewhere, our point P. It's going to have an x coordinate, a y coordinate, and a z coordinate. So let's say it was something like this. This distance would be b, since that's how far it is out on the y-axis. This distance here would be a, since that's how far out it is on the x-axis. And then this distance here would be c, since that's how far up it is on the z-axis. So that's how we figure out our coordinates. Okay, so that's kind of the basics of points and things like that in our three-dimensional coordinate plane. We can also talk about surfaces and things like that, because if you can imagine equations that used to be lines in a two-dimensional plane now become surfaces in a three-dimensional plane. So talking surfaces, so let's say we had something like y equals 5. That would be a line in the two-dimensional plane, right? That would be a horizontal line where the y value is always 5. But in three-dimensional space, it represents an entire plane. So this would be a flat plane at y equals 5. So if we were going to try to draw this, we'd have our coordinates, or our plane here. And then we'd go out to where y is 5. So this is our y-axis. And then it would be represented by a plane at y equals 5. So it's kind of hard to draw in 3 dimensions, as you can tell. But this plane would extend forever, just being like a flat wall right at y equals 5. Okay, so anything x equals, y equals, or z equals are all going to be planes in R3. All right, so anything that z equals would be a plane that's kind of horizontal seeming along the z-axis. Anything that's x equals is going to be something like this, but over here on the x-axis. Okay, so that's kind of the main idea there, with those being surfaces, them being planes in the third dimension there. What if we had some other kind of equation that was not originally a line? What if we had something like x squared plus y squared equals 1? That used to be a circle, right? And if we specify what z is, like if I say, and also z equals 3, then it is a circle. So if I say x squared plus y squared equals 1, that's typically a circle centered at the origin in two-dimensional space, right, with a radius of 1. And that same is true, except it's no longer centered at the origin if we stick in there that z is also 3. In this case, we would go up to 3 on the z-axis, and we would have a circle. If you can kind of, well, it would be a little bit more disc-looking than that, but if you can kind of envision a circle laying flat there, it might look a little bit more like that. But anyways, that would represent a circle. But if we just left it, what if we didn't specify z? If we didn't specify that z is 3, well then, so if we just had x squared plus y squared equals 1, without specifying z, you end up with kind of an infinite cylinder. That stretches on forever up and forever down as well, because we didn't specify what z is. It's just this cylinder that's sitting on, like, right on the z-axis there, with cross sections that are made by x squared plus y squared equals 1. The cross sections are all circles with a radius of 1. So here we end up with a cylinder, and here we end up with a circle, because this is just one cross section of this same cylinder. Anyways, so those are some examples of surfaces that we will encounter in three-dimensional space, and what their equations involve. A little bit later on today, once we talk about distance and stuff like that in three-dimensional space, we'll also talk about what the equation of a sphere would be like, and how we can identify the sphere equation and how we can kind of derive that, or at least get it, switching formats and things like that. I don't think we'll have, that's probably about where we would end. But anyways, first, the next thing you guys are going to be asked about is distance, the distance formula in three-dimensional space. And the nice thing is it's not really all that different from the distance formula in two-dimensional space. So here we go, distance formula. In R3. Okay, so first off, we're going to define distance. We're going to use P1, P2. So it's going to look kind of like absolute value of P1, P2. This means distance between P1, which is going to have x1, y1, z1 for its coordinates. And then P2, which is, you guessed it, going to have x2, y2, z2 for its coordinates. So the distance is going to be represented by the formula, this big square root of x2 minus x1 squared plus y2 minus y1 squared, which is just the two-dimensional distance formula, and then plus z2 minus z1 squared. Okay, so it's not overall all that different than the two-dimensional distance formula. In fact, you're just sticking an extra term in there, z2 minus z1 squared. Okay, so I'm not going to go over too many examples there, just because hopefully we know how to use the distance formula at this point, since we are in Calc BC here. And this isn't all that different than the two-dimensional one, like we've said. Okay, the last thing that we need to talk about for today is the sphere equation. Because now that we're in three-dimensional space, we can start plotting three-dimensional objects and things like that, including things like spheres. So here we go. Okay. So this sphere is going to have a center of H, K, L, and the radius is going to be lowercase r. And this is going to look a lot like the circle equation, actually. It's fairly analogous to in that the distance formula, we stuck in a z term here. Same kind of thing is going to happen with the sphere equation. With circles, it's x minus h squared plus y minus k squared equals r squared. Very similarly here, the sphere is going to be x minus h squared plus y minus k squared plus z minus l squared equals r squared. So then if the center is the origin, then you get x squared plus y squared plus z squared equals r squared. Okay. So this one, we will do an example of the kind of thing we're going to be asked to do for this particular type of problem. So here's our example. We're going to be given x squared plus y squared plus z squared plus 4x minus 6y plus 2z plus 6 equals 0. And we're going to put this thing into standard form and find the center and the radius. Okay, so you may remember from maybe your pre-calculus course or something like that, doing something similar to this, but with circles. You were given something like x squared plus y squared plus 4x minus 6y plus 6 equals 0, and asked to put it in standard form for a circle. The same kind of process is going to apply here. We're going to be completing the square, basically. So what I would do for these is bring the things with x in them together. So we're going to have some rearranging here, x squared plus 4x, and I'm going to put it in parentheses and leave a bit of space. And then I'm going to do the same thing with the y's. So I'm going to have y squared minus 6y, leave a little space. And then z squared plus 2z, leave a bit of space. And then I'm going to move this plus 6 over here over to the other side and have that be negative 6. And now we're just completing the square on all of these. So if we remember that process, that's where we take the number here. So this is a 4. Oh no, the video froze. There it goes. This is a 4. We take that and we divide it by 2 to get 2. And then we square it. And that's what we add right here. 2 squared is 4. So we add 4 there. And then since we added 4 here, we also have to add 4 on the other side. And then this negative 6, we take and divide that by 2. And we square it so that we get plus 9. And since I added 9 here, I also have to add 9 there. And then lastly, 2 divided by 2 is 1. 1 squared is 1, so I have to add 1 there and add 1 on the other side. Okay, and then we can factor these. So basically this one becomes x plus 2 squared. This one becomes y minus 3 squared. Whatever this number is here, that's what's going inside there. And then we have z plus 1 squared, and then we add all of these things together, and negative 6 plus 4 plus 9 plus 1 is 8. So now we have it in standard form. That's part of our answer. And then we can grab the center here and the radius. So the radius is going to be, well, the radius squared is 8. So the radius is the square root of 8, or 2 root 2 if you simplify it. And then the center is going to be -2, +3, -1. Okay. So that's how we do that. Again, we put all the x's together, put the y's together, put the z's together, complete the square for each of these terms, making sure that we add whatever we added in here on the other side of the equation. And then we write them in their squared format, so factoring them, or following the rules of completing the square, you can just take whatever was here and put that inside with the x and square it. And then from that, now that we've got our standard form, we can grab the radius and the center pretty easily. Okay, so that's kind of a basic introduction here to three-dimensional space. That's all we're going to talk about today so far. And your guys' homework assignment is going to be in the Stewart Calculus book 12.1, numbers 1 through 18, I guess 1 through 17 odd, since I'm only assigning the odd problems. But anyways, and so remember, the video assignment here is going to be due on, or like watching the video and everything is due on Thursday next week, since we've got our 5-day weekend here. But the textbook assignment isn't going to be due until Friday, but I will probably add a couple of problems to the assignment next Thursday. So get as much as you can done before we come together on Thursday, so that we can talk about it and answer questions and things like that. All right. Have a great 5-day weekend. Have fun with your three-dimensional coordinate system.